Well, just as I had mentioned in the last class, in this class I am going to discuss fugacity of pure liquids or pure solids. Remember one thing, the starting equation is the same in this particular case as well. What is the starting equation? The starting equation just I had mentioned several times earlier. It is ln f by p equals to integral 0 to p v minus r t by p dp. We start from this particular equation, but we must remember that we are dealing with a liquid. So, how to perform the entire integration starting from 0 pressure, where usually all substances they exhibit they are in the gas phase and they exhibit ideal gas behavior. From there I would like to reach a pressure where the substance has undergone a phase transition from the vapor phase to the liquid phase, and then it remains in the liquid phase from the saturated vapor pressure to the pressure where we would like to find out the fugacity of the pure liquid. So, therefore, to calculate and whatever I discussed, the same thing is applicable for a pure solid as well. So, therefore, to calculate the fugacity of a liquid or a solid at any given temperature and pressure, what do? We break up this whole thing into two parts. The first part, it gives us the fugacity of the vapor phase from 0 pressure to the saturated pressure, such that this gives us the fugacity of the vapor phase under saturated conditions, right. And after that we have another part which extends from P saturated to P, which gives us the fugacity of the condensed phase. And we need to remember that when we have in this particular integration, we get the fugacity of the vapor at the saturated condition. Under this condition, we know that the vapor and liquid, they are at equilibrium. So, therefore, this is nothing but equal to FL saturated, fine. So, therefore, what do I do here? To find out the fugacity of the condensed phase, I simply break it up into two parts. The first part gives us the fugacity of the saturated vapor, which is nothing but equal to the fugacity of the condensed phase under the saturated pressure conditions. And then if my particular or the condition of interest is far removed from the saturated pressure, then we need to calculate the additional fugacity which is generated by compression of the condensed phase from the saturated pressure to the pressure of interest. So, therefore, this can be written down as, I can write this down as RT ln F saturated by P saturated. This part can be written down by F saturated by P saturated, and then the other part can be written down as P saturated to P V condensed phase dP minus RT ln P by P saturated. I can write it down very much in this particular form. Now, removing all the logarithms and writing it down, we can write it as Fc, this is nothing but equal to P saturated phi saturated exponential integral P saturated to P Vc by RT into dP, right, where this is the saturated vapor pressure. This phi saturated, it is nothing but equal to, phi saturated is nothing but equals to the fugacity of the vapor under the saturated state divided by the pressure under the saturated state. Well, this is the equation that I have mentioned here. So, this is the fugacity of the condensed phase, and I would like to recall that this particular expression has been derived starting from the same equation, the defining equation of fugacity with the supposition that the fugacity is equal to the pressure for very low pressures. So, we have started from very low pressures and we have assumed that under this condition the gas, the substance is in the gaseous state and the gas is an ideal gas. So, therefore, what we did, what is the path of integration? The path of integration is compressing the ideal gas from 0 pressure to the saturated pressure, where it becomes a saturated vapor. Under this condition, the saturated vapor and the saturated liquid states have got the same fugacity, and so therefore, whatever fugacity value I get in compressing the gas from 0 pressure to the saturated pressure is the fugacity of the liquid under the same conditions. Then there is an additional fugacity generated because the liquid has to be compressed from the saturated state to the state of interest. Now, here I would like to say that suppose we are dealing with very low pressures. Now, let me write it down in the next page and then it is going to be easier for me. Fc equals to P saturated phi vapor saturated, it's better written as phi V saturated exponential P saturated to P V condensed phase by RT into dP. Here also I would like to make the correction, this is phi V saturated, this is also the vapor phase saturated, right. Now try to observe this particular equation. What do we get? The first thing we get is fugacity of a pure component at temperature and pressure. Suppose the temperature and the pressure is not very high, then in that case the gas can be assumed to behave ideally. When the gas is assumed to behave ideally, then in that case its fugacity and the pressure are equal under saturated conditions, as a result of which this term it becomes equal to 1, right. So, therefore, this is basically it is a deviation of saturated vapor from the ideal gas behavior. Next, we look at this exponential term. This exponential term arises because the liquid or the solid for that matter with whatever we are dealing, that is at a pressure P far removed from the saturated pressure. Now, at conditions which are much remote from the critical, very frequently a condensed phase can be regarded as incompressible, as a result of which we see it is not a function of P. Under that condition, the exponential term can be written down as V c P minus P saturated by RT. We can write it down in this particular form. The other thing which is important is that usually, but not always, these two correction terms they are negligible, because unless P is not far removed from P saturated, this particular correction term, which is usually known as the Poynting correction factor, this correction factor it is not very high if provided the temperature is such that P saturated is low. Under that condition, if P saturated is low, then phi V saturated is almost equal to 1. And we find that if the pressure is not very high, then Poynting correction factor can also be taken as 1. Just to give you an idea regarding these two correction factors, I have a table and a graph with me. If you observe this particular table, what do we see? Here I have taken it from the book of Prushnitz, and there we have found out that the Poynting correction factor for the condensed and the incompressible substances in this particular case, we find that for 1 bar pressure, even for 100 bar pressure also it is not high, but if we are dealing with 1000 bar pressure, then it becomes really high. So, therefore, this implies that the Poynting correction factor becomes important when we are dealing with condensed phases at very high pressure. So, under that condition, this particular term, this term is important, otherwise it is not very important. Even if you observe the variation of the fugacity coefficient with reduced temperature, what do we find? We find that at conditions close to the critical, for those particular conditions, the fugacity coefficient differs remarkably from unity, and we find that as we go for lower and lower reduced temperatures, the fugacity coefficient almost approaches 1. So, therefore, this implies there are two things which are important. One is 5V saturated, it differs considerably from unity as the critical temperature is approached. So, under this condition we cannot neglect 5V saturated. The other thing is, if you observe 5V saturated is always less than 1. This particular term 5V saturated, it is always less than 1, which implies that this correction term, it tends to decrease the condensed phase fugacity, and usually we find that the Poynting correction factor is the exponential function of pressure. This is low at small values of pressure, but it may be very large for large values of pressure or at low temperature. We also find that the 5V saturated, that is also for conditions far removed from the critical, this is also 1. So, therefore, for low to moderate pressures we can safely assume that the fugacity of the condensed phase is equal to the saturated vapor pressure, and when we are dealing with conditions like high pressure or very low temperature or for conditions close to the critical, then we need to incorporate the corrections to the saturated vapor pressure in order to obtain the fugacity of the condensed phase, and these two corrections, they arise primarily because of the non-ideality of the vapor phase and the fugacity generated due to the compression of the liquid phase from the saturated pressure to the pressure far removed from the saturated. Now, before ending fugacity, there is one more thing that I would just like to mention. This is very commonly used for predicting the fugacities of hydrocarbons, and therefore, I have used this particular equation, or rather I have discussed this particular equation. Usually they use the Redlich-Kwong equation of state, which is given here. You already know it with the constant values given in this particular equation. Now, when we use this particular equation, we find that the expression of fugacity is given by this equation, where we find that fugacity coefficient, it is a function of z, it is a function of Bp, and it is a function of a square by b. So, therefore, if we know these three quantities, we would be in a position to find out f by p. Now, usually we can use this analytical form to find it out, but there is one note of caution which we should remember while using this equation, that is the value of z that we are using here, that should be calculated from the Redlich-Kwong equation of state, which I have already mentioned here. It should be used with the Redlich-Kwong, we should be calculating z from here, and we should not be using any particular experimentally or observed value of z, or we should not take z from any other equation or chart in this equation if we want to get a correct value of the fugacity coefficient using Redlich-Kwong equation of state. The other interesting thing is that this also I had discussed earlier, since we know that Redlich-Kwong equation of state is a cubic form. So, therefore, it can be used to predict the fugacities of a saturated liquid as well as a saturated vapor. If you are solving this particular equation, if you are solving this particular equation, we know that we get a cubic value of, or rather we get 3 roots of z. Out of those 3 roots, the largest value that corresponds to the saturated vapor, the smallest value that corresponds to the saturated liquid, and the intermediate value that we get, that has no real physical meaning. The only problem of finding out the fugacities of saturated liquid and vapor using this cubic form of Redlich equation of state is that in this particular case usually the Bp that is an unknown. So, therefore, how to find out Bp from this particular equation? For this we use the concept that the vapor and liquid are in equilibrium under the saturated conditions. So, how do we go about doing it? What we do in this particular case is, in this particular case what we do is, we first go about we use this particular equation. In this particular equation we try to find out Bp by, rather we assume different values of pressure and we try to find out the Bp values such that we use it to find out the fugacity of the liquid phase, we use it to find out the fugacity of the vapor phase, and then we choose that particular pressure as the actual pressure in which we use that particular pressure under which the fugacity calculated for the liquid phase and the vapor phases are the same. Once we have identified the pressure under which the liquid phase and the vapor phase pressures are the same, then we know that the Z corresponding to that pressure should be used here, or in other words the Bp value which we have obtained from this particular equation is then used in this equation, and then we obtain the roots of Z, and then the higher value is taken as the saturated vapor and the lower value is taken as the saturated liquid. Now, other than that, just like I had shown you the Lee-Kessler plots, we find that solving this particular equation and the equation for Z, we can generate a set of curves which can give us the fugacity coefficient in terms of the Redlich-Kwong parameters, which are a square by b and Bp. And we know that that these two curves have been plotted under two conditions. One is the low range of Bp, for which in this particular graph we have shown the fugacities of both the liquid and the vapor, and this is for the high range of Vp, under which condition we have shown for only the vapor phase. For this particular low range of Bp, this is applicable for Bp less than 0.20. For this condition, this graph is drawn, and then this is primarily for coexisting vapor and liquid regions, and this is for higher values. Now, in this particular case, using the charts are much simpler as compared to using the equations. For using the charts, it is very easy. We first have to evaluate the two parameters a square by p and Bp. Once we have evaluated this from the temperature, pressure and the criticals of the system, once these are evaluated, then we read the charts and we using the aforementioned values, and we try to find out the fugacity coefficient for the condition of interest. We can use this for finding out the fugacity coefficient for both the condensed phase as well as for the gas phase. So, therefore, here I would just like to mention in conclusion, since Redlich-Kwong equation is used very frequently to find the fugacity coefficient in the case of hydrocarbons, we can use the analytical equations, but they are quite tedious, but they are accurate. On the contrary, if we use charts, the charts are simpler to use. We just need to find out, as I have already mentioned, we need to find out the parameters a square by b and Bp from temperature, pressure, conditions and the criticals of this system, and then read the charts using this aforementioned values. Here I would also like to mention that the Redlich-Kwong equation is less accurate compared to the Pitzer correlation. particularly in regions of coexisting vapor and liquid. But since these equations have an advantage of being completely analytical and they satisfy conditions of critical isotherm at the critical point, so therefore, under these conditions these equations are quite useful. With this, I end my discussions on the fugacity, on the concept of fugacity, the importance of standard states for a correct estimation of fugacity, reframing the equilibrium conditions in terms of fugacity, estimating fugacities for gases, estimating fugacities for liquids, a practical method of estimating fugacities for hydrocarbons, and after this we go to discuss mixtures, their properties, fugacity of a component in a mixture, and after that we go for discussing the ideal solutions and the non-ideal solutions. Well, just one particular example or one particular problem has been provided here to find out the fugacity coefficient for a van der Waals gas. You can use, or rather you can try this problem to find out the value, and I think it is pretty straightforward. You will not get stuck up in this, but in case you get stuck up, we are there with you. Thank you very much.